In this video, we're going to be looking at the concept of free fall motion, which is the motion of falling objects. What are we going to do? We're going to define the term free fall motion. We're going to look at the history of the theory of free fall motion, explain why it took so long for us to develop such a working theory. Also, we're going to compare free fall motion to other forms of accelerated motion. We're also going to look at the properties of free fall motion and look at problem-solving strategies for free fall motion. Why are we doing this? Because much of the motion in systems that we're going to see, at least on the planet Earth, are rooted in the concept of free fall motion. The concept of free fall motion plays a key role in our understanding of how the universe works in our present theories. Most people also don't understand when it's appropriate to look at a system as if it's a free fall or if it should be something else. Also, human nature doesn't always evolve as much as we like to think, and the history of science's past often shows and explains behaviors of today, particularly relating to scientific findings. And understanding these behaviors best enables us to become better informed with the information that is available. The first concept of relating to falling objects and an explanation for why things fall and move goes all the way back to ancient Greece in the time of Aristotle. Aristotle would make basic observations about the behavior of various things and try to come up with a theory. He had always noticed that rocks have a tendency to fall, and if rocks were to land in water, they would sink. However, water often stayed below the air, and when there are air bubbles in the water, the air bubbles would rise to the surface. Now, when the rocks reached the floor of the lake, they would stop moving. When the air bubbles reached the surface of the lake, they stopped moving as well. He also noticed that fire always has a point that points upwards. And if you were to tilt the stick or match, not that they had matches at the time, but tilt whatever it was that was burning, the flame would always point upwards. He also recorded on how the sun seems to always move in a circular arc across the sky, starting up in the east, which is our sunrise, moving across the sky, being in the middle at high noon, and setting in the west. However, he also noted on how the Earth itself never seems to move, so it is the sun that moves across the Earth's sky. And if you were to take prolonged observations of the night sky, you would see that the stars themselves don't remain stationary, but they actually spiral in the night sky. So, from these observations, Aristotle developed a model of the universe that he believed was appropriate for the data that he had, or the observations that he had observed. He had figured that the Earth itself, being mostly rock, was in fact the center of the universe, and all things move around that, which makes sense when you take a look at how the sun moves in a circular arc across our sky and how the stars move in circles as well. He also believed that the Earth itself was actually committed out of 4 basic elements that were stacked one on top of the other. The rest of the universe moved around us. Now, we know this model is not correct. However, with the information that he had available at the time, it does kind of make sense. For the very simple reason, his observations are totally correct. Rocks fall into water and they sink. Air bubbles are placed in water and they rise. Flames always point upwards. And we can see that the flame and smokes rise through the air. So it is natural to come up with some sort of system like this. And of course, we see everything in the sky moving in a circle around us, and we never observe our own Earth moving. Now, why does this happen from his point of view? What explanation does he have for this? Well, he had developed the idea that there were 4 basic elements that existed on Earth, and it was the Earth itself, or stone, We have air, water, and fire. And what happens is each one has a particular place or realm in the universe. The very center realm, the very core of the universe, is the Earth. Water rests on top of the Earth in its particular layer. Air's layer is right above the water, and then the realm of fire is above the air. And all motion can be broken into two kinds of motion. We have what's called natural motion. This is where objects move on their own to go back to their realm. So if I have a rock that's up in the air, the rock, being part of Earth, is in the wrong realm. It's in the realm of air, and it doesn't want to be there. So the moment you let go, the rock falls. And once it hits the Earth, it stops moving because it's in its proper realm, and there's no need to move. Heavier objects, being made of more rock, will pull on you harder trying to get to the natural realm because there's more rock there. Which also suggests if I have a light rock and a heavy rock, since the heavy rock pulls harder, it will move to the Earth faster than the lighter rock. So it was also believed that heavy things will fall faster than lighter things. Another type of motion was violent motion. This is when you physically force an object out of its natural realm. So if there was an earthquake or a volcanic eruption or some other type of violent event where a rock is hoisted up into the air, then it was believed that you gave that rock some motion called impetus. This is the amount of motion an object has. And that rock will eat up the impetus as it moves, similar to, if you will, the gas in a car tank, where as you're driving, you burn up the gas, and then when you're out of gas, you stop moving. Well, the moment the rock burns up its impetus, it stops moving upward, and now natural motion will take place, and it will fall back to the earth. Once it reaches its realm, it will stop moving because it's back in the place that it belongs. So all motion is either natural or violent from Aristotle's point of view. You don't need to give any impetus for natural motion because objects just want to be in their own realm. Please notice that if I strike a fire and I force a fire to exist down on the earth level, the fire rises up into the sky and then we just stop seeing it move. If I force air underneath water, it rises to the surface, but the air bubbles then reach the surface and they pop, but you don't see the air bubbles move anymore, so there's no more motion there. As for the sun and the stars, they never stop moving. So their motion really can't be natural or violent because if it was natural, they would not move because they're in their realm. But it can't be violent because they never transition anywhere else. So his rationale was for everything that's not on the earth, there must be another element, a fifth element called Althea. Now, this is a very special element that you can never find on Earth, where this element always wants to be in motion and it always moves in circles. This also suggests that we could never understand anything about the universe because there is no commonality between the Earth itself and where we live and the remainder of the universe. This makes us very unique and very isolated. And understanding anything outside of where we live is actually impossible because you can never experience or study it really. Now, Aristotle was during the time of ancient Greece, and like many things during that time, his work was lost for quite some time. Later on, it was rediscovered by way of the Christian religions going into Greece, and his work was found. And they were extremely excited with finding his model and his explanations because this model offered quite a few things for them. The first thing it offers is, in their mind, scientific proof that there must be a deity that created the universe. For the simple reason, when you look at this model, which was scientifically proven through observations of falling rocks and air bubbles, we can see that the universe is perfectly shaped. Everything is in a circular pattern, and everything is segmented out where everything has a particular place. This level of organization and perfection could only exist, scientifically speaking, if there is a deity involved that made this happen, because things just wouldn't be this organized. Also, please notice, by scientific evidence, we can see that all the stars and planets move in perfect circles. Now, circles are not a shape that happens naturally on their own normally. They have to be done artificially. This is considered the most perfect shape. Well, the only way that everything could be in circles then is if there was an intelligent intent behind its creation. So that again, there must be a deity that created the universe. And since my religion was the religion that found this scientific proof of our deity, we must have been destined to find that proof. Thus, we must be the only correct religion, scientifically thinking, based on the scientific model that was found. So churches often love this, and many church religions actually invested a lot of effort into scientific findings for the sole purpose of proving scientifically that their religion is the one correct religion. Also, if we take a look at how things happen on Earth, we can see that there is a caste system here. Earth belongs with Earth. If you put Earth anywhere else in any of the other realms, it falls back to where it belongs and it stops moving. If I take fire and I submerge fire into any of the other realms, that fire moves back off into another realm. It returns back to where it wants to go. Thus, if we are going to be good people and follow the natural order, which was designed by the deity that created the universe, we should follow the universe itself. And so society itself should be cast in such a manner. And if you think about it, back in the times of the pre-Renaissance, we actually had a very strong caste system. Royalty will marry royalty, and the peasantry cannot move up, and everything is in a caste system. And if a peasant thought that they could be better at ruling, then they were not just a traitor, they were evil. Also, there was a hybriding between the church and the crown. They worked hand in hand. And that is because this system supported a caste system that was rooted now in a religious belief. This also then gave rise to the concept of divine right. Because, let's be honest, if there is a caste system here, then royalty was meant to be royal. And if I was born king, well, then I have the right to do whatever I want because I was divinely chosen. It's not like a peasant could move their way up into the ranks of society. If I wasn't supposed to be king, I would have been born a peasant and someone else would have been born into the royal family. And so all of this runs and stems from the scientific proof, quote unquote, derived from Aristotle's model of the universe. Then along in the late 1600s comes along a guy named Galileo. Now the story is, one time while Galileo was in church, he was incredibly bored during a sermon and noticed that the pendulums that they have that swing incense back and forth, he observed on how the swinging of the pendulums were the same regardless if there was a lot of incense in them or a little. This suggests then that heavy objects and light objects fall at the same rate. This doesn't sound like a really big revolutionary idea, but this already now starts to call into question the concept of natural motion, where heavy rocks should fall faster than lighter rocks because of their caste system and being in the wrong realm. So he starts doing some experimentations with pendulums, various masses, various amplitudes, various lengths of string, and he had scientifically shown through experimentation that the only thing that affects the period swing, the time it takes to go back and forth, is the length of the pendulum, and the actual mass has no impact on the timing, which means the mass has no impact on the rate at which the pendulum swings. Now, he's not saying that this is a falling object, but whatever makes you fall makes the pendulum swing. So perhaps the mass does not play the same role as was originally thought. His findings were actually questioned, though, or challenged, I should say, because of the very valid argument, this is not a falling object. And he agreed. The bottom line is, we know that when a pendulum swings back and forth, there are really two forces acting on the bob or the bottom part of the pendulum. We have the force of gravity pulling downward, which is something that they did not consider at the time. There was just some tendency to fall. They didn't know why. But we know it's the force of gravity, which is an external force on the pendulum. And we have the tension force of the string pulling to the fulcrum point, or the point where the string is attached to the ceiling. Now there is also another tension force pulling down on the ceiling, because the tension is an internal force for the pendulum string ceiling system. So that actually plays no effect in the actual motion of the pendulum in terms of the acceleration of the system. However, the force of gravity does play a role, but this is not a falling system. But this starts to then lead to the concept of gravity later on. So, what does he do to address the challenge? He comes up with another type of experiment. It'd be great to just drop an object straight down and measure the timing, but objects fall so quickly, and the timing is such a small period of time that it's nearly impossible to get good data without some sort of electronic device to measure. And this is the late 1600s. So video cameras and stopwatches and photogate detectors are just not even considered at this time. In fact, such suggestions would be considered heresy. So instead what he does is he constructs a ramp, and he has on the ramp various bells that will ring when a ball rolls by them. And he rolls balls of various masses down the inclines. And he listens for when the bells ding, and he starts to space out the bells so that he hears a ding at the same time interval. So if it's ding, 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 that's too fast. So he goes ding, 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 ding. And the only way he gets a consistent timing between the bells is if the bells are not evenly spaced, but actually where the space of the bells gets larger and larger and larger. That also is very significant, because according to Aristotle's model and natural motion, what we would expect is that the objects would just fall at a constant velocity. Small objects or light objects would fall slowly, and more massive objects would roll fast, but at a constant velocity or constant speed. What Galileo found out was that the spacing increases. The speed is not constant. In fact, the distance between the 0 bell and the t equals 1 bell, and the distance between the t equals 1 bell and the t equals 2 bell, this distance here was 3 times that first distance for the first interval. The distance between the t equals 2 bell and the t equals 3 bell was 5 times the distance of the very first bell. He observed the law of odd numbers here. Also, regardless of the mass, the spacing and timing was the same. So something that was very heavy or something that was very light, there was no bearing. This completely debunks this entire theory up here that would have been predicted from Aristotle's model. To make matters even worse, he starts setting up ramps that are shaped almost like a U, where the ball would roll down the ramp and up the other side, and he would notice that the ball on the other side would reach pretty much the exact same height that was released at. Well, that kind of makes a little bit of sense, except for the fact that according to natural motion, once the ball reaches the bottom, it should stop moving, and it should not move up on its own because that would be unnatural. That would be violent motion. The ball up here is in the wrong realm and of course wants to reach the bottom, and so it does. Once it reaches its realm, it should stop. It should not go up the ramp unless something gave it impetus to go upward. For that, there needs to be an act of violence or some outsider said to throw the ball upward, which would be, in a way, a violent act. But there's none of that here. The ball reaches where it should be, and for some reason it goes across and then goes back up into the realm it doesn't belong in on its own. In fact, to make things even more confusing, he starts turning the U into a shape where one side becomes flatter and more shallow. And he notices that the ball doesn't roll up the same distance, but instead rolls up to the exact same height, or at least as close as possible to the starting height. So then he goes, well, what happens if I roll the ball down a ramp and then it's just a perfectly flat surface where it never goes back up? If these balls seek equal heights, my starting height on one side has to equal the starting height on the other side. And if I have to travel a longer distance to do so, I'll travel a longer distance to get to that same height. And I never reach that second height. When would I stop moving? Because experimentally, it is suggested that you would never stop moving. And this again flies in the face of the concept of natural and violent motion, which was the basis of Aristotle's model of the universe. This actually lays down the foundation work for Sir Isaac Newton and his law of inertia. See, Galileo was able to make an experiment to show inertia, but Galileo was not able to explain why this happens. Newton, however, through his concept of inertia, does in fact show that, where once you set this ball in motion, unless there's an external force to stop the motion or change the motion, there's going to be no change. And so there is some external influence that makes the ball go down the ramp. But then as long as there is no external force, such as friction or anything, acting on this ball, the ball would never change its motion afterwards. One of the things that Newton once said that's one of my most favorite quotes is actually, if I see farther than other men, it is because I stand on the shoulder of giants. One of the things that makes Newton so famous is his great myriad of investigations and scientific findings in many different areas, from forces and motion to gravity to light to sound to mathematics. And one of the things that people really misunderstand about Newton is he didn't invent all of these concepts on his own. He had found the work of people before him, people like Galileo, where they started something but they could not finish it. And he was able to take their work, merge it with the work of others, and yes, his own genius, and come up with the working theories and explanations. So this is one of the reasons why we always take a great look at the people who played a role, because science is a step ladder. And even the rungs all the way back to Aristotle, where his theory is completely and utterly wrong, plays a key role in the ladder that we use to climb our knowledge upwards. So Galileo comes up with a different model where the Earth is not the center of the universe, but it actually is the sun. We have the planets that move around the sun. Now, this was also because of other investigative work that he has done observing the night sky. Now, if you notice, he still has everyone moving in a circle. One of the reasons is, well, Galileo believed that there is a God. He believed that God made the universe. He believes that God is perfect, and so the universe would be geometrically perfect, so everything would have to be circular. Galileo at no point actually tried to attack religion. In fact, he himself was a very religious individual. But this model that he came up with really risked to disrupt the social order. Keep in mind, there's a lot of stuff invested in how society is built off of this model. Remember, scientific proof is a key thing for how we behave. So again, Aristotle's model gave quote unquote scientific proof that there is one correct religion because one religion found this model, and based on its organization and quote unquote perfection, shows beyond the shadow of a doubt that there must be a deity. And since we are the ones who found it, it must be our deity, and so we are the correct religion. Also, again, it has that caste system so that we can now turn around and place poor people with poor people, powerful people with powerful people, and we can justify never allowing the poor to move up in their society for the very simple reason if they were meant to lead, they would have been born in the right class. And again, it justifies divine right. Because if I wasn't supposed to do the stuff I was doing as king, I would never have been born king. After all, look how organized the universe is. It's just science. The new model, however, totally contradicts the original model. This means if this model is not correct, how do we can then say that our religion that found this model is the one correct religion? Perhaps our religion is correct. Maybe it's not correct. This is crazy. This is a threat to where we are in society. Social implications. There's no caste system here. The universe is ordered, but there is no caste system. So are caste systems then a natural event, or is it a social human construct? If it's not natural and a social human construct, then perhaps the poor can work their way up. Perhaps those people who were not born as royalty could lead. And perhaps there is no such thing as divine right. And if there's no divine right, then why does the crown need the church to endorse them as heavily? So there is a lot of potential implications that could upheave the way that society operates, just from this new model of the universe, suggesting that the old model that society is built upon is in fact wrong. In fact, it would be entirely possible that perhaps one day there could be a country or a nation where people don't rely on birthright for leaders. In fact, it could be one where the people themselves choose those who will govern them. In fact, they might even turn around and sever an official religious tie where any and all religions would be accepted. In fact, even the possibility of having no religion whatsoever or questioning the validity of any religion. This is definitely flies in the face of how society was scientifically thought to be, or scientifically should be. So Galileo's theory is a real threat to the social order. The reality is, they did everything they could to silence Galileo's work at the time. If we had social media back in the 1500s, and you were to try and look up any of the work here on falling objects by Galileo, you would get all of these little warnings on how this study is in dispute, or how this is fake news, or this is misinformation, for the very simple reason it was a serious threat to all the powers that be at the time. They didn't have social media at the time, but they did have the Spanish Inquisition, and Galileo was actually brought before the Inquisition and brought to the torture chamber where they displayed the instruments. They didn't actually physically torture him, not to my knowledge, but they did display the instruments, which was a classic tool that they would do. They show you all the different wonderful things that they will do to you if you are not willing to recant your statements. And, well, being the smart man that he was and not wanting to go through all the torture, he actually did recant his findings, saying it was only just a theory and there was no real substance behind it. They released him, and he had continued to do his work. He got to the point of doing direct experimentations on falling objects. He went to one of the tallest buildings at the time, which was the Tower of Pisa. At this time, it was not a leaning tower, it was actually standing straight upwards. And he would drop objects from the very top to the floor, and he would measure the timing that it took for the objects to fall. And again, he scientifically showed that light objects and massive objects, or heavy objects, fell at the same timing. The rule of odd numbers showed itself yet again. Objects are speeding up as they fall. They fall at the same rate regardless of their mass. The concept of natural motion does not work. It does not apply here. It gets to the point where he actually does a mental experiment to prove his point. And it was a really simple scenario. It was, if I have an anvil that weighs, let's just say 100 pounds, and I tie a 0.05 pound feather to the anvil, and I drop it at the same time I drop a 100-pound anvil by itself, which one would fall faster? Which one would hit the ground first if they were dropped at the same time from the same height? Now, this should be a very easy question to answer based on the theory of natural motion. And if we look at this, heavier things fall faster. That's the premise. And so if we look at this as an object, we can view this here as heavier than this. 100.05 pounds is greater than 100 pounds. So since heavy things fall faster, this must hit the ground first, for no other reason than the fact that it's heavier. And that makes perfect sense. And Galileo goes, cool, great. But the feather and the anvil really aren't one object. They're actually two things tethered together. So it's a lot like if you had two runners. The feather falls slow because it has a lot less mass or weight than the anvil that would fall fast. So it's kind of like if you had a three-legged race where you had a slow runner with a fast runner tethered together. And on the single anvil, I just have a fast runner. So what should win a race? A fast runner who runs on their own, or a fast runner that's tethered to a slow runner? Well, the slow runner was going to hold the fast runner back. So the fast runner should come in first place. So the anvil on its own should fall faster than the combination because it's not slowed by a smaller feather. But the anvil and feather combined weigh more than just the anvil, so it should fall faster. We have two contradicting answers using the exact same premise that heavy things must fall faster. When that happens, it often shows that the premise itself is flawed and wrong. Galileo showed beyond a shadow of a doubt that all things fall at the same rate and that they speed up as they fall. His problem again was, while he found this out, he could not offer any explanation on why that was. It was Newton again who was able to make the connection. Newton, with his concept of the force of gravity and his second law, came up with a very simple and elegant explanation. He had turned around and said, well, we have a force of gravity pulling down on each one of these objects. And the heavier object will have more mass. Mass resists the force of gravity. So with a larger mass and a larger force of gravity, I would come up with the exact same acceleration, because acceleration is the ratio of the external force over the mass of the object. So my acceleration of gravity would equal the force of gravity over the mass of the object. It's kind of like if I was to ask the question, what would be the easier boxing match to win? Would it be a heavyweight fighter in a heavyweight boxing bout, or would it be a lightweight fighter in a lightweight boxing bout? Which one would have an easier time? And the truth of the matter is, neither one does. Yes, the heavyweight fighter often deals with an opponent who is stronger, but the heavyweight fighter is also heavier and stronger. The lightweight boxer often deals with an opponent that is not as strong or as heavy, but then neither are they. There is a natural balance here. And so Newton had said that heavier objects or heavier systems feel a greater force of gravity pulling down, trying to create a large acceleration, but they also have more inertia to resist that larger acceleration. So the acceleration turns out to be the same for all objects, regardless of their mass. One of Newton's great advantages over Galileo was, again, the timing. Galileo was at the very beginning of the Renaissance period, so it wasn't very much enacted at the time. And in the late 1500s, for his findings, the church had placed him under house arrest for the rest of his life. Newton, however, was almost 100 years later. He was in the full-blown peak of the Renaissance period. He was free to do these kinds of investigations. He was encouraged to publish his findings. And so he was able to make the connections that Galileo was not allowed to do because he was underneath no threat. In fact, he was encouraged and enabled because of the timing to actually do this kind of research. So we have the theory of free fall. This is if an object is falling freely, which means only the force of gravity acts on you, nothing else, then all objects falling will accelerate at the same rate tangentially, regardless of their mass. And again, this stems from Newton's second law. It's a very simple concept if you think about it. And it sounds even kind of obvious. However, it is a concept that took a very long time to actually come into be, more than 100 years, because of the social implications that it risked or implied. In fact, Newton's work showed that free fall acceleration depends only on the mass of the planet or moon that you're on, pulling down on the object, and the size of that planet or moon. So for all objects on the planet Earth, the average acceleration that they fall at is 9.8 meters per second squared downward. However, if you were on the moon, it would be 1.6 meters per second squared downward. Saturn, it would be actually greater than the Earth, and Pluto would be incredibly small, regardless of the mass of the object that's actually falling, because I don't make me fall. The thing pulling on me, for example, the Earth, makes me fall. And the Earth makes me fall at 9.8 meters per second squared because of the quantity of Earth and the size of the Earth pulling on me. Since the moon is a different mass and different size, it has a different acceleration of gravity. Free fall acceleration is a vector. It has a direction as well as a magnitude, 9.8 meters per second squared for Earth, downward. If we were to write this out correctly, we should say it's a sub g, a for acceleration, and either have an arrow to suggest that it's to show that it's a vector, or have it bolded out in print. And we would say negative 9.8 meters per second squared, because the negative means down. However, a lot of times you'll see textbooks work with the letter G as a positive 9.8 meters per second squared. They're working with a scalar value instead of a vector value. Why is that? Well, because they haven't talked about vectors yet. They like to wait months later on to talk about vectors because it might be too confusing in the upfront to do so. I actually find not talking about vectors first makes things very confusing. So we will always work with negative 9.8 meters per second squared because that is going downward, and we're going to call it what it is, which is a vector. One of the things that people will be confused with is the difference between free fall and real fall. In fact, there are people who are around who think that heavy things fall faster than light things. After all, if I drop a hammer and a feather side by side, the feather hits the floor last. But then that's because there's air resistance. This was actually shown on one of our moon landings. In fact, it was our first moon landing where one of our astronauts took a feather and a hammer and dropped them on the moon. Now, the moon doesn't have an atmosphere, and we can actually see that the feather falls at the same rate as the hammer. They hit at the same time. Free fall is a real concept that we don't often really work with on Earth because it takes place in a vacuum. Only gravity acts on the object, nothing else. However, if there is small amounts of air resistance for short periods of time, we'll pretend the object is in free fall. It's free fall enough. The error is going to be so small, it's not really worth the effort to try and make it as accurate as possible. However, when air resistance is substantial, I definitely cannot make this pretend. And so we have to use something else because real fall, there we go, real fall is not the same as free fall. Now, since free fall motion is in fact accelerated motion, our kinematic equations, our big three kinematic equations, will always work. What some people do, though, is they rewrite the equations in terms of the y-axis, where instead of saying position final, they say height final. Instead of saying just acceleration, they'll say AG. And this really should be bolded out and vectored because it is actually a vector, where AG is, of course, negative 9.8 meters per second squared. If you notice, really these three equations that we have for kinematic motion that we've always worked with, and these three equations here are literally the same format, all the same plus signs, all the same squares. The only difference is literally adding the letter G to acceleration and replacing position with the term heights. For this reason, I never work with these equations over here because I am provided with these three equations. The AP will provide you with these equations. Your college professors will often provide you with these equations, and we are working with them so often, I'm probably going to have them internalized anyway, so I don't need anyone to give them to me. So I'm going to just work with these three equations as is. And if you're telling me it's free fall, A is just negative 9.8 meters per second squared. And height is a position. So I'll just use whatever height you give me for the position, and I just run from there without any big transition. However, your textbooks and other websites and other teachers and some tutors often like working with the acceleration g, which is 9.8 as a positive sign, 9.8 meters per second squared as a positive. So they have to take the big three equations and rewrite them completely with negative signs for subtracting out the 9.8 effect. This often confuses people because now you have a whole new set of equations you have to work with. And then to make things even nicer, if you're taking the AP, if you're taking a college class, they often don't give you these equations. So now you're used to thinking of a whole new set of equations and you've doubled your workload and you're not going to be provided with them. And again, it's easy to look at the differences, but if you focus on the commonalities and the similarities, your life often will be a whole lot easier. So I often consider taking this type of approach, focusing on all the differences, to be a very bad idea, just because it makes my life way more complicated. Bottom line is, if I can understand how to work these three equations of motion, and I'm willing to accept that down is a negative vector direction, I can easily solve for any free fall motion as an accelerated problem because, shocker, it's an accelerated problem. One of people's biggest problems understanding free fall is identifying free fall problems. Most people think, well, if I just drop an object and I let it go, that's a free fall problem. And that is true. However, there are other cases of free fall as well. One of the best ways I can think of explaining this is by the very simple question, can Buzz Lightyear fly? Now, if you've seen the movies, you know for a fact that he doesn't really fly. As Woody once said, he falls. He falls with style. And so if I take an object and I drop it, that is definitely free fall. And that's because when I let go of the object, the only force acting on me is the only thing acting on the object, I should say, is the force of gravity. However, if I throw a ball upwards while the ball is in my hand, it is not in free fall. But the moment the ball is out of my hand, the only force pulling on it is the force of gravity. There's no impetus force pulling the ball upward. The ball was given a velocity because I threw it. I exerted an external force on the ball, setting it in motion. And now it will remain in motion unless an external force such as gravity stops it from moving. But that takes time. So the ball is actually falling as it moves upwards. That's why it slows down. Once it reaches the top, it then comes back down and we see it speeding up, but it's actually falling the entire time. That's not intuitive for most people because when I hear the word fall, I think going down. But you can think of it almost like a person who has millions of dollars, but they have no income and they just spend money. The question is, are they going to become poor? And the person who's got millions of dollars can turn around and say, no, I'm rich, I'm fine. You're not rich because without an income, you're going to hit zero. That's what we have here. The ball is moving upwards, but it's in denial about its falling. Eventually, it's going to try and buy something and it's going to have absolutely no cash available and things are going to crash really hard for them. This object was falling the entire time. The requirement for free fall is not the direction that you move, but the forces acting on you. And the only force acting on the ball on the way up is the force of gravity pulling downward. The only force acting on the ball on the way downward is the force of gravity pulling downward. The ball was falling the entire time. If I shoot a basket, then that basketball travels as a parabola. But the only force acting on that ball once it left my hands is the force of gravity. So again, this is free fall motion. It doesn't look it. If I think this is free fall, then I believe that Buzz Lightyear flies. And all of this is very unique and very complicated. But the reality is, it's all just falling. This guy, I like to say, falls in denial. This one falls with style. If I have a satellite that orbits the Earth, the only force pulling on the satellite is, in fact, the force of gravity. The satellite itself is also in free fall. This is why we do not need engines and motors and fuel to keep satellites in orbit. We need to get them, use the engines and the fuel to get them up into orbit. But once in orbit, there's no power. And for the very simple reason, I don't need power to fall. Gravity is making me fall. The satellite's issue on why it doesn't crash into the Earth is because it moves sideways so much, it keeps missing the Earth. But we will get into that type of motion later on. But all this motion here is free fall. Our big takeaway from this thing is, if gravity is the only force acting on you, no matter what it looks like you're doing, you are actually falling. Here we're going to take a look at a couple of sampled problems on our problem-solving strategy to solve for a free fall problem. And they're going to be the exact same strategies that we used with accelerated motion. The big hiccup for most people with this type of problem, though, is the amount of information you're not given. And you're not given a lot of information because we know a lot of information. There's the big difference. Since this is free fall motion, we already know the acceleration. So we don't have to solve for it, and we never have to be told what it is unless there's some special circumstance and where the acceleration will be different. So here I have a problem where I have a ball that's going to be thrown upward with a speed of 30 meters per second, and I want to find the maximum height it reaches before it falls back down. And right away, people get gummed up on this going, okay, well, I know I'm looking for maximum height, so I'm looking for position final. And I know my initial speed, or my initial velocity, is 30 meters per second positive because I was thrown upwards. But I don't know anything else. How am I supposed to solve for this? But we do know quite a few other things. For example, when I throw the ball upward, what is its speed at the very top before it just comes back down? Objects always stop before they fall back down. Even if we were to take a look at a velocity versus time graph here, we would see a positive velocity that reaches 0, then negative. This means right over here, if this is a velocity versus time graph, the object has to stop moving. So my velocity at maximum height is 0 meters per second, and this is at maximum height. I also know the acceleration, because while I was thrown upwards, I'm falling. So that must be negative 9.8 meters per second squared, because this is on the planet Earth. Now, some people will love to make the argument, I was never told what planet it was on. Fine. But since we haven't colonized any other planet or moon yet, if we do not tell you it's on a different planet or moon, it defaults to the planet Earth. So I'm going to now just take the stuff that I was given, which was the initial velocity, positive 30 meters per second. I know the ball started on the ground, so my initial position is 0. I know that my acceleration is negative 9.8, and maximum height, again, the velocity is 0. I'm at a critical point. So the question is, looking at my big 3 equations of motion, which one am I going to use? And I'm not going to focus on these over here. Again, I'm given only the big 3. And since I'm looking for velocity, and I do not know the time, this makes my selection pretty easy. Out of my 3 equations, which is the only one I can work with when I do not know the time? That's the time-independent formula. So I'm going to just simply plug in the values and solve for the height. Please notice the height comes out to be a positive value. That makes sense since I traveled upwards. And my position is a vector value, so it should be positive to show that it was above the ground. Here I have a ball that's thrown upwards at a speed of 49 meters per second. Again, I was given the direction upwards, so this is going to be a positive velocity. How much time does it take to reach the maximum height? In this case, I don't know what the maximum height is. I'm just looking for the time it takes to reach maximum height. Again, I'm only given the initial velocity. I'm given nothing else. But again, there's stuff that I already know. For example, I know the acceleration is negative 9.8 because again, it's falling on Earth. Maximum height means that the velocity at that maximum height is 0 again. And I can declare my starting height to be the floor, which is 0 meters. So looking at this here, I'm looking for the time, which means the time independent formula does not help me at all. And I can either work with the position formula or the velocity formula. And since I do not know position final, I really can't work with this one. So I have to work with the velocity formula. So I can now just plug in my values, and again, I solve for time. And in this case, my time comes out to be a positive, which makes sense because time can never be a negative. If you come up with a negative time, it suggests the following things. The first thing, you might have made a mathematical mistake where you forgot to do a sign or forgot to flip a sign when you cross over the equal sign. So double check your work and make sure you haven't done that. Or you're looking for something that's mathematically impossible. If I was to turn around and ask for what would be the speed or the velocity of this object when it's been in the air for, let's say, 89 seconds, and it can't be in the air for 89 seconds, and I solve for the time, I'll often come up with a negative time because it's an impossibility. So if you come up with a negative time, first check to see if you haven't made a mathematical mistake, and then look to see if it's physically possible, because sometimes we ask for the impossible. Our last question, I have a ball that's thrown upwards with a speed of 49 meters per second, and I want to find out how much time it takes to reach maximum height and now to return back. This question is very much like the last one, except I now know one other piece of information. The starting position and the final position have got to be the same since the object returned. So if I declare my starting position to be 0, my final position is also 0. So I have my initial velocity of positive 49 meters per second because it was thrown upwards. I have a starting position and final position of 0 meters because it lands at the same height it was thrown at. And I have an acceleration of negative 9.8 meters per second squared because while it might be denying the event, it is falling. So the question is, which equation can I use? And right away, I can remove the time-independent formula because it doesn't have time in it. And since I have both the initial and final positions, I can probably work with the position formula. So I can plug in my values, and I see this time I have a bit of a quadratic. But the constant is 0, so I don't have to use the quadratic formula. I can factor out a t. Once I do that, I can find 2 times. One of the times is the obvious t equals 0 seconds, because that's when the ball started on the ground. And this formula will now give me the 2 times it reaches the ground. And it starts on the ground, so the first time is 0, and it's useless to us. The second one is 10 seconds, which is double the 5 seconds to reach maximum height. The motion here is symmetrical. The time up and the time down are going to be the same for the very simple reason I have the same acceleration on the way up as I do on the way down. So the rate at which my velocity slows down is the exact same rate that my velocity will speed back up. And so that's going to be a very big thing. So for an object that's thrown up into the air or even a parabola, projectile, which is just thrown up into the air, the acceleration up and the acceleration down are always equal, which is always the acceleration of gravity, which is always negative 9.8 meters per second squared on the planet Earth. If I am launched from the same height that I land at, then we have special things about time and my velocity. The time up and the time down are going to have to be the same because the acceleration affected me the same way on the way up and the way down. Also, if I have the same time and the same acceleration, then the change in velocities will be the same. So if I lose 49 meters per second squared going upward, so I gain a negative 49 meters per second squared, then from 0 I will gain another negative 49 meters per second squared on the way down. So the velocity down is going to equal negative 49 meters per second squared. I'm sorry, negative 49 meters per second. So the velocity up and the velocity down are always exact opposites, or the speed up and the speed down are equal, but in opposite directions. This is only true if the starting height and ending heights are the same. The acceleration is always true no matter what. Another approach I could have used to solve this question then by use of the symmetry of velocities is I could have used the velocity formula. So if I knew that the final velocity was negative 49 meters per second by way of symmetry, I could just use the velocity formula, which is mathematically easier than the position formula. And if I had solved for the time up, knowing 5 seconds, I could have just used the symmetry there and said 5 up plus 5 down is 10 total. All right, that's going to wrap us up here. There is a lot of information here. The historical context is important for our understanding on how society reacts to scientific theories and how the powers that be will often try to silence scientific theories that are politically or economically unfavorable. However, that's more for your own edification. Most of the stuff we're going to deal with is the actual physical properties of free fall. And again, there was a lot here. So if you have any questions on this, we'll be happy to address any of that stuff in class. If this just makes perfect sense, you're going, oh, so this is just accelerated motion like we've been doing. You are well ahead of the game. Again, if you feel that you need a little bit of help on this, you're exactly where you need to be. And if you're struggling with the material here, that's totally okay. We have plenty of time to work with you on this because again, as always, these videos are not about me getting out of my teaching, but only give you experience of the material before we actually look at it in class.